So, so today we're going to concentrate on the Hilbert space, okay? So this is going to be the second part of our Hilbert space discussion. And let me remind you, yesterday we introduced the notion of an adjoint operator, and as Gifre kindly reminded us, now we're dealing with a physical Hilbert space with a physical theory, so we're not complexifying anymore. So Z bar makes sense as Z star. We're on the real slice. And we define the vacuum as a state that has to be annihilated by all operators with m greater or equal to -1. Likewise, from the adjoint definition, we can also conclude that the out vacuum has to be annihilated by all these guys. And of course, now if everything is real, so the SL2R algebra generated by these guys annihilate the vacuum. This is an important assumption, otherwise we don't have a conformal field theory. Oh, because now we are considering the generators with only real coefficients. The algebra is the same, of course. The difference is just in what we think about the coefficients we're putting. Okay? So yesterday we also decided to consider unitary theories. Okay. So here in the Hilbert space, it translates into saying that we have positivity of norms. Now, unitarity in Minkowski space translates into something that is called reflection positivity in Euclidean space. And that's, as you know, we are working in Euclidean space. So really, when we talk about unitarity or imposing unitarity, we're imposing that condition called reflection positivity. Okay? So just by looking at the condition of unitarity, we found the following. If you consider the state constructed from the vacuum by acting with L-2, and we consider its norm, now we're doing it backwards from what we did yesterday. Okay? So we consider the norm of this state. The norm would be this. But of course, if we commute these guys, we're going to get 0. So we can replace this by the commutator. And by looking at the Virasoro algebra, we see that the first term will have an L4, which is going to be killed by one of the two vacuums. And we're only going to end up with a central charge. And therefore, we conclude that it has to be greater or equal than 0. So we're going to try to make a plot of the constraints imposed by unitarity on the possible values of the central charge and on the conformal weights of our states. So right now, we know that we can discard all this, which is a region of negative central charge. Okay. So we also discussed yesterday that we can think about constructing representations of this algebra, and this is where mathematicians can come and help us, because it's a completely mathematical problem. It has really no physical input, except for one thing that I will ask you to think about. So in constructing the representation theory, we assume there is a highest weight state that we call H. Okay? And it's defined as follows. It's an eigenstate of L0 with eigenvalue H, and it's annihilated by all ln operators with n greater than 0. So we also drew an analogy between the structure of the L's and a more familiar example, which is SU2. And we said that ln's with n greater than 0 were somehow raising operators just very much like J plus in SU2. L minus n, again with n greater than 0, were lowering operators. Like J minus, and L0, finally, was like the element in the Cartan subalgebra, just like J3. Okay?
Freddy?
Yes.
The group analytic in the vacuum is SL2C.
Yes.
Not SL2R. No, that's what he.
Well, the only difference is what you do. At the level of the algebra, they are exactly the same, right? The only difference is what you choose to multiply by. It could be complex or...
You're allowed to multiply by complex coefficients, even when...
Now here I want to consider, I'm only considering now a physical theory. Okay?
And there you're allowed to multiply by complex coefficients. So
no, because I now, my conformal transformations, my global conformal transformations are acting on the cylinder, right?
Do you agree that the global conformal transformations are a six-real dimensional group?
The ones acting on this part are SL2R, okay? On what we're doing with the L operators. So, do you agree that if we have the L bar operators, we will have another copy? And 3 plus 3 is 6. Okay, so let's go to the representations. Okay? Now, starting with the highest weight, so here will come the question that I want you to answer. And I want you to answer the question today, okay? So it's not going to be homework. So just as we did with operators, we're going to classify the states in our representation as follows. We're going to start with the highest weight. We're going to call that level 0. And the dimension is going to be, of course, the eigenvalue of the L0 operator acting on this. And in this case, is H. So the next states will be this. This is going to be level 1. And we have H plus 1. At level 2, H plus 2. L minus 1 is squared. And we can also have L minus 2, and so on. So now when we go to our mathematician friend, if you went to the PI day yesterday, all of you did, right? Because you were supposed to. So if you go and ask Kevin to help us with the representation theory of the algebra, and you say, well, I want to start with the highest weight state, and then construct these things and classify all possible representations in this form. One question he could ask you is, why do you want to start with the highest weight state? When we have Lie algebras, right, the reason people always tells you that you start with the highest weight state is that you want to find finite dimensional representations. But here, our representation is going to be infinite dimensional anyhow. So he could ask you, well, why do you want to start with the highest weight state?
Where else would you start?
Sorry?
Where else would you start?
Why do you have to start somewhere? I mean, you could have something that is infinite dimensional on both sides.
I mean, is there some interpretation of the highest weight state as like having the spectrum boundary?
Well, the answer somehow is already on the blackboard. So what happens if this guy was not annihilated by these guys?
Yeah, so you need a bounded spectrum.
Exactly, exactly. So remember, the dimension maps to the energy of the state. Okay. So if we allow this guy to keep going up, the energies are going down. So our theory will not have a spectrum that is bounded from below, and we usually think that those theories are not consistent. Okay. So that's the only piece of physics that we have to tell Kevin, and then the rest he can do the rest. And indeed, mathematician did the rest, so we can just benefit from the rest. So this is a number of states here, okay? And I'm going to write what the number is, and the reason is that it's going to be useful later on. So it's clear that the number of states there is the number of partitions of the integer n into two non-zero integers. Well, positive integers, really. Okay? So the counting is something that is a very classic problem. And this thing has a beautiful generating function, which is of the form okay. So this is a generating function for these numbers, and that's what we're going to take as a definition. Okay, very good. Now, I was careful to write here that this is a way we construct a representation, okay? But usually, what are we interested in? What kind of representations? Well, unitary representations, that's one thing. Irreducible. It's always good to find irreducible representations, right? Now, is this irreducible? Well, we don't know. It could be, it couldn't, maybe it's not. So in general, so when we have this thing that could be a collection of irreducible representations, this has a name, turns out to be a modulo, and it's called the Verma modulo. And our job is to find when this object is an irreducible representation. Okay? And if it's not an irreducible representation, how to identify the reducible parts and get rid of them. Okay? Okay, but before we do that, let's keep going with unitarity. And now consider the norm of this state. I mean, I'm changing the notation a little bit here. Just to save notation, I'll just use one bar. Okay? So the norm of this state, of the first descendant of the highest weight state, again, we can write it like this. Right? Now this time, our friend here will contain a factor of L0. Sorry, and this is not on the vacuum. And therefore, we're going to pick up a factor of H. So by assumption, I mean, if we don't start by assuming that this is positive, then we're going to be in trouble. Okay? Let's assume it's strictly positive, and imposing that this is positive implies, or at least not negative, that this is non-negative. Okay? So we can also forget about all this part of the space, as well as this, because this is the part where H is negative. Okay? So we have reduced everything just to one quadrant in the space. Okay. Now, how could this thing, how could this infinite dimensional object become reducible? Well, the reason could be because maybe some linear combination of states at some point behaves like the highest weight state of another module, right? So what's the definition of a highest weight state? This. It's an eigenvalue of this, but all these guys are eigenvectors of L0. So all we need is to find some linear combination that will be annihilated by all these guys. If we do, then such an object could be called the highest weight of another representation that is sitting inside this representation. Okay? So searching for, how shall we call them? I don't know, for the lack of a better name, they actually have a name, but the name will not mean anything unless I tell you some properties that they have. So I don't want to tell you the name now. I'm not sure this one means more than the other, but at least it will not leave you thinking about why we chose that name. Okay, so we just have to start searching at each level for these objects. So what's the property of the object? Well, let's say at level 1. Can we find something at level 1? Well, at level 1, there is only one state. So we have to impose, remember, we are searching for things that do the following. So this is what we need, okay? Well, if this is true, let's just consider the case L1. It must be true for this. But if this is the case, if this is the case, then by writing this as a commutator, we learn that H must be 0. Okay? So we find that at level 1, the only chance we have of having this guy becoming a new highest weight is when H is equal to 0. So it's actually possible, but it's a little bit of a degenerate case. Okay? So we have that at level 1. For several reasons, this is not going to be very interesting, but let's move on to level 2. Let's see. Let's do it here. Maybe not. So you all remember this definition, right? It's very standard. You learned this in high school, right? When you count the number of partitions of a number. So I like to say only in Russian high schools. Okay, so searching at level 2? Well, at level 2, we have two states. So we're looking to construct a state which could be a linear combination of these guys. So let me find out what kind of linear combination I want. So I want to consider this state. Okay? And I want to ask whether it's possible to find an alpha such that this guy will become a new highest weight. Okay? Well, what do we do? All we have to do is to check an infinite number of conditions. Okay, so we better get a start because we have one. So we start with this guy, and we have to impose that this is 0. This is what we need. Okay. So L1 on this once again, this guy annihilates H. Right? Because H was the highest weight. So we can replace this by a commutator. So we're going to get the commutator of L1, L minus 2, plus alpha L1, L minus 1 squared, acting on H. So the commutator of L1 with L minus 2 is easy to read from the algebra. It's just 3 times L minus 1. The commutator of L1 with L minus 1 squared is L minus 1 with L1, L minus 1 plus L1, L minus 1, L minus 1. And if we do the algebra, we're going to get 2 times L minus 1, L0 plus L0, L minus 1. Okay? So we can now apply these operators on H. And we get that L1 acting on our state chi is, if I'm not mistaken, is 3 plus alpha times 4H plus 2. Okay. So how do we get the factors of H? Well, because we have L0. Okay. Well, again, we're assuming that chi is not identically 0. So if we want this to be 0, we need this to vanish. So we need alpha to be minus 3 over 2 times H plus 1. Okay, so we're done with the first case. Only another infinite number of cases to go. But let's go with the next one. L2. So we also need L2 on this thing to be 0. Yeah, I also did that one. So you have L2. Again, we can replace it by commutators. So we have L2 with L minus 2 plus alpha L2 with L minus 1 squared acting on H. And this time, this is trivial to do, so I'll leave it as an exercise. Well, let me give you an intermediate step. You get something that looks like this. The interesting thing is that now, given that you have L2 and L minus 2, we're going to get information about the central charge. So the central charge is going to appear in the condition for the first time. Okay? And therefore, this thing becomes and again, we need this to be 0. And we conclude yes. That's right. Or maybe, I guess we can sort. So from here we get 4 plus 2 alpha h plus c over 6. Right. That's correct, right? So the point is that from here, I should be able to derive that C has to be 4 times 2 plus 3 alpha times h. But it doesn't look like that. So probably I made a mistake here. Okay. Well, let's figure that out. All we need is this coefficient. That's the one that I think is wrong, right? So we just have to figure this out from here. And we get L2 with L minus 1, right? With some L minus 1 here and also on the other side. So this guy will give us, it will be 2 minus 1. Sorry, 2 minus minus 1. So it will be 3 times. So there is this 3 that I'm missing here in this calculation. So this is probably a 6 too. And somehow I ended up missing this 6 is not a 6 actually. It's probably a 2. And that comes from the fact that in this guy, when we look at the central algebra, we have C over 12 times, so this is n equals 2, so you have 2 times 2 squared minus 1. So I have no idea what I was doing when I got the, well, I just probably copied the 2 numbers in the wrong place, in the incorrect place. So this is a correct condition for the central algebra. Okay. Now, using what we found for alpha, if you put it in here, you find that C has to be this quantity. So has anybody double-checked what I did there? This quantity over here is right? Okay, great. Okay, now we found this condition.
I'm not sure about the first one.
You mean this?
No, the L1.
No, L1, yeah, L1 is correct.
Yeah, but from the one, they are inconsistent, those 2 lines. There's a 4H, the H plus 2, and
Really?
2H plus 1.
No. That, oh. Well, that might be the.
I think
That should
it's
be a 2H
2.
plus
In the alpha, it says to be 2H plus 1.
Oh, yes.
H plus 1.
Yeah, so you see I had it here. So, yes, I forgot it here. Okay. Great. So, very good. So that's what happens when you don't do it with Mathematica. Okay. Now let's look at this thing. Okay? This is a curve in that space. Right? Well, let's see what this curve does in the space. Well, the first thing we notice, or at least that we should be able to notice, so we want to plot this in the upper quadrant, okay? So if you take C as a function of H, and you take a derivative, you find that it has a maximum at C equals 1, okay? So C equals 1 seems to be a special point. Clearly at H equal to 0, now we're looking at the plot sideways, right? Because it's a little easier. We're thinking about C as a function of H, okay? So we look at it sideways, and we see that it has a 0 precisely at H equal to 0, and it also has a 0 at H equals to 5/8, right? So let me put 1 here. So half should be here, a quarter, and then we have 3/4 here, and therefore we should have, so this one, 5/8 should be there, and this is where the other 0 is. Now what we have to find out is where the maximum is. And the maximum happens to be, if you do the calculation, it happens to be at a quarter. Okay? So we're just going to cross our fingers and without Mathematica hope that this is smooth. Of course, you can also plot it and check that it's something like this. Now, something interesting happens, right? Well, I won't mention it now. Let's keep it like this. So clearly, this curve is separating the space into two regions, right? Because remember, for us, our space is only the upper quadrant. So something happens here, and something happens outside. And that's what we're going to find out. All right. Now, this state has a chance of doing what I said it should do. So the exercise for you is to do the other infinite number of cases that we're missing. Okay, show without imposing any other conditions, right? Because we don't have, the only two parameters we had were the central charge and the dimension h. So for the values we already found, it better be that this is true for every n without imposing any other conditions, okay? So you should find that this is true. Now there is an interesting observation, which is that already with the properties we found, what is the norm of this state? Well, to calculate the norm of this state, what we do is to take this guy with L2 plus alpha L1 squared, and so this is the adjoint of the state, and here we can put our state. Sorry? Okay. Well, but we already checked that L1 kills the state, and L2 kills the state. So we get 0. Okay. That's why these states are called, and that's the name I didn't want to give at the time, these states are called null states. Okay. Now, there is something else that is interesting. With this property, this guy has something else with respect to the rest of the states in our representation. What happens when you dot this state with any other state in our representation? It's orthogonal to everybody, right? So this state and its descendants are orthogonal to all other states at the same or higher level. Okay. Now, that's a reason why we can think about this really, or the whole set that we have, as the direct product of two vector spaces. Okay? So we can separate from our original set the vector space generated by this guy and all his descendants, and think that that vector space is not there. Okay? Now, once we get rid of that guy, what do we have to do? We have to keep searching for other ones, right, at higher levels and so on. Okay? Now, of course, if we are not sitting on this curve, this state will not be a null state. Okay? So we're assuming we're sitting on that state, and then we keep searching for more states that look like this. Once we get rid of all of them, the representation that we're going to get will be an irreducible representation. Okay. So in order to do that, we have to develop more technology, or we have to find a good mathematician to help us do it. That's even better. Okay. So let's consider a more general procedure, a more systematic. So if you have some vectors in some vector space V, okay, there is a simple way of determining whether these guys satisfy any linear relations of the sort that we're looking for, and it's by constructing something that is called the Gram matrix. Let's call it M. Remember, here we are not assuming that our space even has a positive definite metric. That's what we want to do, right? That's what we want to find out. So at the moment, we don't have to impose it. So we can have states with zero norm, and we could also have, in principle, states that have negative norm. In fact, so we only found some consistency conditions, or the consistency conditions to have a chance of getting something that is unitary. But we have to check it. Okay? It might be that we need more conditions. So here, what we're going to do is to construct this matrix of inner products sorry, we don't need the dot. I put already there. Okay. So we consider this matrix, and the determinant of the matrix has information about linear dependencies. Okay? In particular, if the determinant vanishes, then we definitely have the presence of a linear dependence. if the determinant is negative, we then have the presence of at least one negative eigenvalue, which means that at least one state has negative norm. And therefore, this determinant could also tell us about unitarity. Okay? So this determinant, again, at level 2 is very easy to calculate. So let's do it. So what are the states? So V1, let's say that is this vector, and V2 is this vector. Okay, so we're going to beat the level 2 to death here. We're doing everything with it, just because it's the only one that can be done in reasonable time. So we have to calculate this. This is part of something we already calculated. And we want to finish this. So this matrix happens to be this quantity, okay? So if one of you is very good in mathematics, it would be great to write a code that can generate these matrices. See that they only require the Virasoro algebra, right? So it should be fairly straightforward to automate this. So the determinant of this matrix factors as follows. Okay. So it has a 0 at h equal to 0, and that's the one that we found at level 1. Right? That's a null curve we found at level 1. And it has this part, but this part, if you solve for C, if you ask this to be 0, and you solve for C, guess what you find? You find exactly the condition we got earlier. Okay? So you find precisely this curve. But in general, it's easier to think about it's easier to think about C as a function of H, okay? So it's convenient to think about this as the product of 3 roots, or the product of 3 monomials with roots that depend on the central charge. And I think there is a factor of 32 here if you factor out the 16 with the 2, okay? So the first root is h equal to 0, and the other 2, they are trivial to calculate. Let me write them down nevertheless. So 2 and 3 are 1 over 16, 5 minus c, minus plus 1 minus c, 25 minus c. So if you plot this, the 2 branches, one branch will give you this, and the other branch will give you the other one. So people like to say that this is related to the first root, the second one, and the third one. Okay? Very good. And now is where we need our mathematician to come and help us, because we would like to understand the structure of this matrix and compute this determinant at any level. Okay? Now, see something interesting here. This guy was the null state at level 1, right? And it showed up at level 2 too. Well, that makes sense, right? So at every level, if something was a null state at a higher level, it should also show up at a lower level, right? Just because that guy will have descendants, right? Very good. Okay. So here is our mathematician friend, Victor Kac. And he computed these determinants for any n. And that's why they have his name. So at level n, there is a constant that is not important for us. Not only he computed the determinant, he computed the roots, which is even more exciting, because that's the thing that we want to plot over there. So he found the following, that it was nice to classify the roots by the ways of decomposing the integer n, or any number less than n, into products of two integers. And a particular root associated to this partition of p of a number less than n into p and q will come with a power that is a function p we define, but not of n, but n times p, n minus p times q. Okay? So this power is reflecting the fact that if you found something earlier, you're going to find it later. Okay? That's why this is a product over all the earlier ones. Okay? And here is a miraculous formula. Okay, that's the answer. All right, so I thought there were some other color chalks. Okay, at least one. All right, so having the general formula, now we can go and start drawing things. Well, the first observation is the following. Already at level 2, we know that the determinant vanishes here and here, right, on this curve. So what happens when you cross this? What happens to the sign of the determinant? It changes, right? Now it turns out that the sign of the determinant is positive here and is negative here. So when we are in this region, we don't have any chance of getting something that is unitary. Already at level 2, we will have something with negative norm. So this region should also be crossed out. Okay? Now when we go to the next level, we have to draw the same lines and then cross out what happens, right? Well, let me see if I succeed in drawing this. So the next one, so this one is this. Oh, now we can change the notation, right? Here I was using the natural notation for the roots, root 1, 2, and 3. But now we know that these roots will match the general formula, okay? And the roots actually match the general formula if I think about this one as being the 1, 1, this one the 1, 2, and this one the 2, 1. Okay? Yes? Oh, it's not an S, sorry. That's 25. Okay. So you see, we have the product, 1 times 1 is 1. That means that this guy was really at level 1. 1 times 2, 2. 2 times 1, 2. So these are the guys, the new guys we discovered when we went to level 2. Now we have to go to next levels and see what happens. So there is a point that is interesting here, which is a half. Okay. And the reason a half is interesting is that there is a line going from here, going all the way to 1, that meets at this point with this line. And of course, there will be something else that goes over there. Okay? So that line is the 1,3. So you can sit down with mathematics and plot these lines that I'm claiming here. There is another one that goes from an eighth, and this guy goes towards 1 and intersects this one here. Okay? Now it turns out that if you go crazy and you start drawing all possible lines, they only intersect at particular values of the central charge. In fact, for c equals a half, for below c equals a half, there is nothing. There are no intersections. C equals a half is the first time you find intersections, and you can prove that there are only 3 intersections. Okay? So there will be another special line somewhere here at 7/10, another special one at 4/5, and an infinite number of them accumulating here. Okay? Now, why are these things important? Well, the reason is that you see that by drawing crazy lines all over the place, I'll basically discard everything here as possibilities for unitary theories, right? Well, the only points where I won't be able to discard things based on the flip of the sign of the determinants will exactly happen at the points where 2 of the lines intersect, okay? So the points of intersection are the only ones that have a chance of giving us unitary theories. So let me write down what these special values of C are. Okay, these are the special values. And our mathematician friends not only worked out this and the general formula there, but they also worked out the H's happening at the intersection points. And the best part is that the formula is not complicated. Okay? And the values are restricted by the following conditions. Of course, this is supposed to happen when 2 lines intersect, so we should also have another set of P and Qs, okay, not related, not satisfying these conditions, for which this thing gives the same value. And you can see that there is a symmetry here. If you exchange P and M minus P and Q by M plus 1 minus Q. So let's see what happens for M equals 2. M equals 2 is precisely the point with C equals to a half. Okay? So for M equals 2, we see that we have, M equals 3. M equals 2 is trivial. M equals 2 is actually this point with 0 central charge. So for M equals 3, we have these conditions, right? So what are the possible cases? Well, the possible cases are, you can have for P, can be 1 and 2, and for Q, when P is 1, it can only be 1, but when P is 2, it can be 1 and 2. So we have 1, 1, and we also have 2, 1, and 2, 2, right? But by the symmetries that I told you, this one is a place where the H, well, this one is a place where you get the same value of H if you started with the 2, 3, this one with the 2, 2, and this one with the 1, 2. Okay? So I didn't say it, but this line, so let's have a look. So the 2, 1 intersects with the 1, 3. So this must be wrong again. This is correct. So let's have a look. This is what? 1, 3. Which is correct from the picture. Okay. And how about this one? The 2, 2. Oh, I didn't tell you what these guys were. Let me see if I can figure it out. So this line was the 2, 2 line. So the 2, 2 line meets with the 1, 2 line here. So that one is correct. And I didn't draw it, but there is a 2, 3 line going from here. And that's the other one that we find. And those are the only 3 possibilities. Okay? Very good. So tomorrow, we're going to discuss the general OPs. And remember that the idea is to find theories where we can tame the correlation functions, right? So the theory with C equals to 1/2 looks like a great candidate because it seems as if we only have 3 primaries, right? So we'll only have to deal with 3 guys. So from the theorem that we started to prove yesterday and we didn't finish, all correlation functions of descendants can be computed once we have the correlation functions of the primaries, okay? So these particular values of the central charge are going to be important. They are going to give us a chance of carrying out the full bootstrap that you guys discussed during the first 2 weeks. Exactly, okay? In fact, our friends Delavin, Polyakov, and Samolochikov in '84 already identified the possible sets of central charges where you can tame the number of primaries. And they are given by this, okay? And they call these ones the minimal models. Now you can notice that the guys we found are special cases, right? So these are minimal models where you can tame the number of primaries. But if you impose unitarity, they also discovered that you have to impose that n prime is equal to n plus 1. And therefore, you find C equals to 1 minus 6 over n times n plus 1. And this is called the discrete series of unitary theories. Okay? So I was right. Last line, perfect timing. Okay, so tomorrow we're going to see how to use a bootstrap, OPs, and everything to solve all possible theories and do everything that can possibly be done.